Good morning, class. Today I want to talk with you about the extraordinary properties of water. This is chapter 15.1 in your textbook, and that section of your textbook is about water. Now, I want to show you the objectives of today's lesson. And the first is to understand the polar nature of water. In other words, we know that we have a polar ice cap, but what I'm referring to, of course, is that water is made up of a couple of different polar bonds between the oxygen and the hydrogen, okay? And so we'll talk a little bit more about that. We did talk about that in Chapter 8. I also want you to be able to draw a hydrogen bond between two water molecules. Well, I do believe we've actually discussed that before, so again, this will be a little bit of review. But once we understand those first two concepts, then we'll use those to sort of begin to understand water's special physical properties and why they are present. Okay. Now let me go back to the slide, the front slide here, just because this YouTube video gets compressed and sometimes it gets cut off. So again, the extraordinary properties of water, 15.1, and then here are our objectives. And now let's go on to my next slide, which I don't want you to take notes on. I just want to explain to you, why are we studying water? Why is it important to study water? Why does it matter that we study water? I don't need you to know these numbers. I just want you to get an appreciation for why we do this. And so the first thing, of course, is, well, Earth is 75% water. Or it's not 75% water. It's covered by 75% water. It's mostly nickel, actually, in the center of the Earth, and a bunch of lava, basically, a mantle. However, it still dominates our ecosphere. Humans are made mostly of water. Turns out that the average human is about 62% water. Believe it or not, when you're born, you're about 75% water. And progressively, as you grow older, you lose more and more water. So this is true. Humans, as they get older, begin to shrivel up. Okay, almost all chemical reactions involved in life processes take place in water. So all your enzymes, your receptors, the receptors that make you happy in your up in your brain, the ones that make you unhappy, the chemicals, the dopamine, all these types of things, your metabolism in your body, all these millions of chemical reactions that go on your body, all take place in water. Water is the solvent of life. We're going to talk about what that word solvent means tomorrow, but water is the solvent of life. Now, we also know humans need water to survive, and we know that we can go a lot longer without food than we can go without water. Okay, so we need it to survive, so it's important. And for this class, what's exceedingly important is that learning about water and all its properties and its polarity and all these things teaches us a lot of important scientific / chemical concepts. And so this is why we're going to study water today. Now this slide is a little wordy, but it really brings home a very simple point, that water is polar. We've discussed this before. If you have a water molecule, the oxygen is electronegative. The two hydrogens are electropositive. And so we end up getting a shift of the electron density towards the water, okay? And that's what this bottom picture down here is showing, that we get negative electron density here and consequently positive here. We learned about the dipoles in the center structure here, about these bond dipoles, and we actually learned about net dipoles. So we have a net dipole where the negative electron density is sort of on this side. And again, these polar molecules, especially water, they kind of act like a battery. They've got a positive end and a negative end. A positive end is kind of up in this direction, up here, a positive end, and a negative end, kind of like a little battery. And we say that is polar. Now this is important because this type of arrangement with water causes it to end up participating in something we've talked about before, which is hydrogen bonding. So what I've done here is just simply, I have a slide. It says hydrogen bonding in water, but really all it is a couple of pictures. The first picture to your left here is just two water molecules showing you their polarity and then showing you how they interact to make a hydrogen bond. And so here's our hydrogen bond. I'll just write H bond. And I'll also draw an arrow here to a covalent bond, something we've studied. Okay? And one of the things to remember is that if this covalent bond has a strength of 100%, that means this hydrogen bond actually has a strength of 5%. So a hydrogen bond is only 5% as strong as this 100% covalent bond. The perfect analogy is kind of comparing a covalent bond to chain links in a chain, and comparing a hydrogen bond to something like Velcro. And of course, many people say, well, why do we care about a bond that's so weak? Turns out that even though this bond is weak, it participates in so many things and gives water so many interesting properties that really, in a way, water is probably the most important substance other than maybe oxygen for life. And the reason water is important is because of hydrogen bonding. So you could almost say that hydrogen bonding is probably one characteristic that provides us with life. After all, we know that if you have DNA, the double helix is held together by hydrogen bonds between the base pairs. When it replicates, that hydrogen bond, because it's weak, pulls apart and allows you to synthesize RNA and allows it to pull apart and transcribe. So this hydrogen bond and the fact that these bonds can come and go quickly and make a bond and then make a connection then not make a connection is very important. In fact, all the enzymes in your body work that way. Generally, when they come in, they actually usually anchor themselves, like say a target into an enzyme. It binds to an enzyme. It's actually anchored usually by beginning with hydrogen bonding. So this sort of interaction is incredibly important. So now that we sort of got this hydrogen bonding and polarity out of the way and kind of describe the structure of water, let's now talk about how that structure, what kind of properties does it give water. So what are the properties of water? Okay. And first of all, let's get some basics down about water. Let's talk about its boiling point. For that matter, its freezing point as well. The slide says boiling point, but at sea level, pure water does boil at 100 degrees Celsius, and it does freeze at 0 degrees Celsius. These are numbers you should know, and that these are numbers that in the Bay Area are going to be pretty precise because we're pretty much at sea level, very, very, very little change. So again, notice it has to be pure water. Later on, we're going to learn what happens to boiling points and freezing points when you don't have pure water, when you have solutions, and we're going to learn about solutions in chapter 16. So this chapter 15 is really nice way to sort of get us into the next few chapters where we're going. The boiling temperature of water decreases at higher elevations. So I just want you to know the boiling temperature of water decreases at higher elevations. So when you have a lower atmospheric pressure, it's easier for water to boil. This makes sense because after all, what's keeping water from boiling? It's the air pressure pushing down on the water. The more air pressure you have, the harder it is, or the more heat you would have to give, or the more temperature to get those molecules to leave the surface of the liquid. But as the pressure lowers, it becomes easier. Okay? So when you're at a higher elevation, water maybe it only boils at 97 degrees Celsius instead of 100 degrees Celsius. Why? Because the atmosphere is thinner up there. This has sort of an obvious consequence in your life, and I've experienced this firsthand when I spent some time in higher elevations like Salt Lake City where my aunt lives, or I also spent some time in Denver. You find out that the same sort of recipes on boxes and stuff don't work quite as well. And if you look on those boxes, they have the higher altitude directions, and usually that means that higher altitude you need to heat it longer. So this point down here says, for this reason, an egg will take longer to boil at higher altitudes. Why? Because the water is boiling at a lower temperature, so you're not supplying as much heat to the egg, so you need to heat it longer in order to get the egg to boil, so you can crack it and eat it. So keep that in mind. This is kind of a more common sense, sort of everyday type of thing, but something to definitely think about in terms of the properties of water. Now, I've got 5 other properties here that are maybe not as something you would think of every day. Let me go through them really quick. We have cohesion, adhesion, high specific heat, and then something called the high heat of vaporization. This is sort of the energy required to go from a liquid to a gas, and fusion, the energy required to go between a solid and a liquid. And also, at the very end, we're going to talk about the weird density profile. So first I'll talk about cohesion, then I'm going to talk about adhesion, then the specific heat, and then these heats of vaporization and fusion. And then we're going to talk a little bit about the density of water and its various densities and its various states and how that changes. Don't necessarily need to write these down because I'm going to go over each of these properties individually. So the first one is cohesion. And so what you want to tell yourself is that cohesion is the attraction between particles of the same substance. The same substance. And this is important. The key word is same substance. So this is when we're talking about water being attracted to itself. That's called cohesion. Okay. When you get cohesion in various liquids and stuff, it results in a surface tension. And so every liquid has a certain surface tension. And in the case of water, it's a measure of the strength of the water's surface. And one thing with water is it tends to have a very high surface tension compared to most other liquids. Why? Well, think about why. We'll talk about that at the end, but it does. And when you have a high surface tension, you produce something called the surface film on the water that allows insects to walk on the surface of water, etc., etc. There's a lab where you can do, I don't know, maybe some of you guys have done this, where you can take paper clips and you can actually float them on water, on the surface of water, and you can get quite a few of them on water before they'll fall through. There's a lab where you can take pennies and just drop water, and you'd be surprised how much water you can ball up on a penny before it actually runs over the side of the penny. Again, this is basically due to the property of cohesion. With the pennies, it's a little bit of adhesion as well. But generally speaking, it's about the surface film of water. And of course, we've all seen, if you've gone to a pond, you've seen the bugs and spiders and stuff that, technically a bug, that can skate along the surface of the water and they don't sink in because the surface tension of water is fairly high. So again, the key term here is cohesion. Get that definition down, but same substance, and results in surface tension, which is a measure of the strength. And obviously the third one is maybe not, it's sort of a consequence of that, not a big deal. Just so you know what cohesion is, that it's the same substance. Now let's move on to adhesion. And adhesion is somewhat similar to cohesion, but with a slight difference. And that difference is it's the attraction between two different substances, okay? So adhesion is the attraction between two different substances. One of the consequences of this is something known as capillary action. Water molecules will tow each other along when in a thin glass tube, for instance. So if you take water, put a little straw or glass or something, you'll see the water go up, and this is known as capillary action. So this is a process of adhesion where the water is adhering to a different substance, and it's actually, in terms of capillary action, it's actually going against the flow of gravity. So some examples of that are transpiration process, where plants and trees remove water from the soil, And also, you see this every day. If you take a paper towel and you soak up water, you're seeing the process of adhesion, which is kind of a form of capillary action. Okay, so again, adhesion, you know, it's this idea of two different substances. And so really sort out in your mind the difference between cohesion and adhesion. Read about it in your textbook. Understand that. Lots of examples. Not the end of the world if you don't remember any of the examples. I'll show you a picture of capillary action. Here, it's a little demo. But you guys have seen this a million times probably in your life. You take it for granted. But if you think about it, it's kind of interesting. You have a liquid moving against gravity. And so you have this idea where there is, water climbing the structure, okay? But this process of adhesion of these molecules wanting to adhere to each other can override the force of gravity. So, frankly, I think my little capillary action demo there is kind of cool. Straw lowered in water, water climbs the straw. I think that's kind of neat. Again, anyways, you can remember an example of adhesion might be capillary action. So let's move on to the next point, which is talking about specific heat. Now later on in the year, we're going to talk a lot about specific heat. We're going to do a lot of calculations, but water is kind of special when it comes to specific heat. So let's give a definition of what specific heat is. And what it is, it's the amount of heat you need to raise or lower a gram of any substance 1 degree Celsius. So how much heat, and that heat will either be calories or joules, is needed to raise or lower a gram of a substance 1 degree Celsius. So very simple measurement. In the case, let's just go here. In the case of water, turns out water has a very high specific heat compared to most other substances. And for this reason, water resists temperature change both for heating and cooling quite a bit. Okay? And I think you guys kind of intuitively know this. For instance, you know that if you go out on a hot summer day and you see a big bucket of water and you see a piece of metal and they're both sitting in the sun, intuitively you know if I put my hand in that water, it'll actually kind of maybe even be cooler than the outside air, this hot heat that I'm in, or roughly the same. But I don't think I'm going to touch that piece of metal because I think it's going to be really hot. And it turns out the reason is because the metal has a low specific heat, means it doesn't take much heat for the substance, the metal substance, to raise up in temperature, whereas it does for water. So in a way, water is kind of a heat insulator. We use it all the time. Many nuclear power plants create lots of heat where the control rods are. The best insulator is water. They use water to control the heat. And I actually have some numbers here for you. This is water's actual specific heat. It's 4.18 joules of energy is needed to heat a gram of water 1 degree Celsius. So if you have a gram of water, which is 1 milliliter of water, and you want to heat it up from say 20 to 21 degrees Celsius, you would have to put 4.18 joules of energy. Let's compare that to some other substances, like chloroform, another common organic solvent. You see, oh wow, chloroform, it only takes 0.54 joules to go move a gram of chloroform up a degree Celsius. That means water can hold heat 8 times more than chloroform. That's a lot. And finally, let's look at a sample metal, copper. This is a very typical number for a metal, 0.38. Usually they're all less than 0.5. And so you can see copper doesn't hold heat very well. It transmits the heat. So again, this quantity-specific heat in these numbers, again, and that number, 4.18 people, that number is way outside of the range of most other chemicals. So again, water just sort of stands out. It's sort of an enigma. Okay? So with that, let's move on to the next two items, or the next item, which is the high heat of vaporization. Okay, this is another thing that water has that's different from most things. And this is the amount of energy to convert, say, 1 gram of a substance from a liquid to a gas. There's a little typo here I see. This should be of a substance, amount of energy to convert 1 gram of a substance from a liquid to a gas. And so water, my goodness, you need 540 calories to convert 1 gram of water from a liquid to water vapor. So to go from water to water vapor, for every gram you need 540 calories. That's a lot, people. So in other words, it takes a lot of energy to make steam. It takes a lot of energy. It's making steam, believe it or not, is not necessarily very energy efficient. Okay. So vaporization is this convert a gram of a substance from a liquid to a gas. Now, and the reason this is, people, is because in order for the water to evaporate and to leave the surface of the liquid and become a gas, all the hydrogen bonds on the surface must be broken. So in order for the water to evaporate, hydrogen bonds must be broken on the surface. And so again, this must mean that water does a lot of hydrogen bonding, and because it does a lot of hydrogen bonding, more energy is required to get it into the gaseous form. And what this actually means is that water has a very, and again, another typo here, so let me get this right. It means water has a very low vapor pressure, is what I meant to say. It has a very low vapor pressure. So that means it'll take longer to evaporate than most liquids, because it needs so much more energy to break the bonds to become free molecules, free gas molecules, that if you put it in a container, there's not much pressure being developed because not many of the molecules are leaving the surface. Likewise, if you take something like nail polish remover, which is basically acetone with some other chemicals, they have a very high vapor pressure, and so there's very little hydrogen bonding, so these molecules just can leave the surface so easily. And when they do, when you open up the container, you can sense that right away. There's a pressure that comes out and it hits your nose, and you can smell it. It's all these high vapor pressure, non-hydrogen bonding molecules want to become a gas, and so they evaporate quite quickly. And I know people think water evaporates, but trust me, you take a typical organic solvent in a lab, you could put 20, 30 milliliters in your lab, like of acetone or something overnight. You come back the next day, it is gone. Water will still be there. So again, this is due to the fact that water has a high heat of vaporization. Okay, I'll give you another second or so there to finish off your notes. Anytime if I am going too fast, obviously the video can just be paused and you guys can catch up. Okay. So let's talk about heat of fusion. The heat of fusion is kind of the word fusion, I don't know why that came into being, but essentially the heat of fusion is the ability to how much energy per gram is needed to take a substance between solid and liquid. So it's much like vaporization. It's just looking at how much heat does it take to go between, say, an ice cube and water, or water and ice cube. That's called the heat of fusion. So it's that process between melting and freezing. And water's heat of fusion is much lower than its heat of vaporization. It's about 80 calories per gram. Okay, and somehow you have to kind of put that in perspective, though. What that means is in order for ice to melt, each gram of the ice has to gain 80 calories. Each gram has to gain 80 calories. And let's compare that to chloroform, where you only need about 18 calories per gram. And what this means in real life is it really means is that ice, believe it or not, melts very slowly. And I always say this to students, and they don't really think that, but the problem is you've never seen other substances melt. So for instance, if you get something like T-butyl alcohol or deuterated chloroform, and you get them around room temperature, they can be in a solid form, and then you set them out and you watch them melt and you put an ice cube, they melt almost instantaneously. They melt very quickly. Whereas, ice hangs around for a long time. So again, it takes, again, water has sort of this innate tendency to, again, not want to respond as much to heat, and it takes more heat to make things happen with water. Okay, so I want you to look at this slide. This is really near the end of what I'm going to talk about today. And there's just two pictures here. And one of the pictures is of ice and one is of water. And I want you to take about 30 seconds and choose. Is the one on the left ice or water? And once you choose, then the other one's, ice or water. Make your pick. Which one's ice, which one's water? If you need to, talk to a colleague. Okay, does everyone, are your bets in? So let's go ahead and see what the answer is. And here's the answer. Turns out the one on the left is water and the one on the right is ice. Now if you were to look at these white squares, there's sort of these white lines that go around, what you see is that the ice, the solid water, if you will, is actually less dense than the liquid water. This might seem intuitive to you guys, but actually it's counterintuitive. What we learned about matter was that, again, water is pretty compressed, but we learned that usually solids get even smaller and the molecules get closer together. It turns out that water undergoes a very strange reorganization where it makes even more formal hydrogen bonds, and it ends up coming into this sort of hexagonal structure that you see there, and it actually ends up spreading out. A good analogy would be if you were all walking around in the class and kind of bumping each other and pretending like you were water, and then right when I said freeze, you all grabbed each other's hands and stood as far apart, putting your hands while you were still connected, putting your hands as far apart as you possibly could. Okay, and then all of a sudden you'd be rigid structure, but you would be ice. However, if you were chloroform, what would actually happen when I said freeze, you would all end up kind of huddling in a mass as close together as possible, looking like, say, a group of Marines or something like that. So this is actually a pretty significant difference. Very few liquids, there might be some out there, but none that are very common anyways, that have this property where the solid is less dense. The solid is less dense than its liquid. And in that case, it's water. So let's just look at some real-world examples, like, why does it matter that ice is less dense than water? So for instance, every day, hey, we no one wants to have a soda can explode in a freezer. Why? Because when the water in the soda starts to freeze, it expands because it's less dense, so it creates more volume, all the way back to D equals mv, and so actually the soda can will burst. Back in the day, if I had a big beaker of some other type of solvent, I'd put it in the freezer, I'd come back the next day, the amount would actually be smaller in the closed container. Okay, so again, ice is sort of the opposite of almost all other liquids. Pipes, so if you have a home in Tahoe or you live in the northern climates, say a vacation home, and you're not there much during the winter, you have to turn off the main water valve, and then most people turn on their faucets to drain all the water out. Why? Because the water, if there's water inside the pipes, they could freeze and then they'll expand and the pipes will burst. This happens all the time in the winter in a lot of places. Go anywhere in the north and the northeast, you'll notice the potholes on the roads are much worse. Why? Because the freezing and thawing and the water gets into the cracks and then it freezes and it just causes more potholes. Again, much of the erosion that we see has to do with, running water, of course, but again, freezing water up in the upper mountains freezes, it breaks rocks off, and we get lots of rocks seen in mountain streams and erosion. And probably one of the most important concepts, and there's been people that have done studies on this because they know at one time Earth was completely covered by ice, a long time ago, billions of years ago. And we know today now too that basically this property maintains life in lakes and other bodies of water. Lakes don't freeze from the bottom up. If ice truly was if water was like any other substance and was more dense as it became a solid, as the temperature got down, the water itself would freeze and the ice would fall down to the bottom. And eventually the lake would just freeze from the bottom up, and everything in the lake would die every year. That wouldn't be good. I mean, right now, you can go to Minnesota, you can go walk out on a lake, drill a hole in the lake, and you can put a fishing line down there, and I guarantee you, you'll probably catch a fish. So there's still a viable habitat in the middle of the winter in these lakes. We used to joke that if it was the opposite and ice was more dense than water, ice fishing would be pretty easy, because as the lake froze more and more, the fish would end up just sitting on the top of the lake one day. You'd come out there and you'd see fish literally flopping around on the top of ice and a little bit of water. And of course they would all die eventually, and as well as the vegetation. So a lot of people think this property alone really is the basis for life occurring on this planet, which is, when you think about it, a pretty big deal. So what I wanted to talk about here are all these properties: cohesion, adhesion, high specific heat, the high heat of vaporization and fusion, and even this weird density profile. It turns out all of them are grounded in the concept of hydrogen bonding. All of these characteristics are because water has an unusually high number of hydrogen bonds, which gives its unusual characteristics. So again, hydrogen bonding is the key. With that, I believe that's all I have. I just want to thank you for listening, and we'll enjoy the homework that you're going to get now.